Okay, hello everyone. My name is Jonathan Tariku. I'll be presenting this work entitled Multi-Target Tracking in Multiple Non-Overlapping Cameras using Fast Constraint Dominant Sets. This is a joint work between myself, Iyasu, Dr. Andrea Prati, Dr. Marcello Pelillo, and Dr. Mubarak Shah. And this work has been accepted in IGCV this year. So in a typical multi-target multi-camera tracking, we are solving two sub-problems. So the first one is we need to address within camera tracking first. So given these cameras, in this case 3 cameras, we need to address individual tracking in all the cameras. So in this case, these clicks represent a track of a person. So once we have that, we need to identify if a track of a person appears in more than one camera. So this problem also referred as across camera tracking. So here is the pipeline. So the input or the algorithm was detection human boxes, which are generated by a pre-trained human detector. So first we will split the whole video into smaller segments, and then we generate short tracklets in those segments by merging detection bounding boxes into consecutive frames if there are significant overlap which is more than a certain threshold. And then we will use this fast constraint dominant set to merge those short tracklets into a tracklet. And in our second layer, we further merge those tracklets into a track. Similarly, here also we will use fast constraint dominant sets. So once we do this in all the cameras, we will put together all the tracks in all the cameras, and then we will build this bigger graph in our third layer, and then we try to identify if a track of a person appears in more than one camera. Here also we will use FCDSC to solve that problem. Here is a quick demo of within camera tracking. First, we will have this detection on the top left. You can see these detection boxes, which are the input or algorithm. And then we will merge these detection bounding boxes in and generate these short tracklets in each segment. And then those short tracklets are further merged into a tracklet. Finally, those tracklets are further stitched together to find the final long tracks, where we give a consistent ID for each individual throughout the video. Now let's see how we generate these tracklets using fast constraint dominant set in our first layer. So as I said, we will split the videos into several segments where each segment contains, in this case, 15 frames. We have 6 segments here. As you can see, we have this short segment, short tracklets in each segment, and then we will build this fully connected graph where the short tracklets are the nodes, and then every short tracklet in one segment is connected to every other short tracklet in all other segments. And then the edge weights between these two nodes will be computed based on their appearance as well as motion similarities. So once we have this, we will run our algorithm, and it will select this nice cluster where it selects a single node from each segment where that node belongs to the same person. Okay, so we will do this iteratively for all the people. This will be the second cluster, which selects that person from all the cameras, the third one, and then the fourth one. So we note that here in this case, we don't have this hard constraint that we need to select a node from each segment, because in that segment, for example, that person might not appear due to long occlusions or misdetection. So in that case, our algorithm ends up not selecting any node from that specific segment, which is a very important actually property, where in most tracking-based clustering-based tracking algorithms enforce this hard constraint. So similarly, as of the first layer, in our second layer, we will use the same strategy, but the only difference was the nodes will be tracklets rather than short tracklets, and the resulting click will give us a track rather than tracklets, and then we will use similarly FCDSC to generate those clusters. So now let's see on the third and the final layer how we are able to solve this across camera tracking using fast constraint dominant sets. So at this point, all the tracks are being generated in all individual cameras. So these nodes represent a track of a person. So similar colors represent the same person. And then we'll build this fully connected graph. In this case, every other node is connected to all other nodes in other cameras. And then we start with camera 1. And then we ask our algorithm such that give me a cluster which contains one of these constraints. In this case, the constraints are the tracks in camera 1. So after we do that, it will give us this nice cluster where it selects a similar person if it appears in all other cameras. In this case, even this guy, which is a broken track of a similar person during within camera tracking, has been able to stitch together during across camera tracking. So this is the second cluster where it selects this node of this guy from camera 1 and camera 3. Similarly, this is the guy, this guy or girl does not appear in any other camera, so the resulting cluster will be a singleton. So we do this for the second camera as well. This time, the tracks from the second camera are our constraints. And then similarly, we'll find these clusters iteratively. So this one is the first cluster. And then the second cluster, in this case, this guy appears only in camera 1 and 3. We do the same thing for the other ones. In this case, this guy does not appear in any other cameras, so it will result a singleton. Similarly to this guy, it also results a singleton. So we will do, after we do this, we will have these 4 nice clusters. We will repeat the same process for camera 3 as well. So now the tracks in camera 3 will be our constraints. This will be the resulting clusters, okay? So at the end of this process, we will end up with these nice clusters, and then we can easily combine these clusters to come up with a single cluster for all the IDs and solve across camera tracking. So far we have seen how we formalize within and as well as across camera tracking using the underlying clustering algorithm. So let's see how we actually generate or how we can actually find those clusters using the proposed clustering algorithms. So let's start by defining what dominant sets are, what dominant set clustering is. So dominant set clustering is actually a generalization of maximal clique to an edge-weighted graph. Okay, so the formal definition of a dominant set is as follows. So if you are giving me a set S said to be dominant set, which is a subset of a bigger vertex in a bigger graph, should satisfy these 2 criteria. So the first one is all the weights which are in this set S should have a positive weight. So all the nodes should have a positive weight. So the other one is all other nodes which are outside of the set S should have this negative weight, which is less than 0. So these 2 criteria are also referred as internal homogeneity and external inhomogeneity. So in this presentation, I will not address how to compute the weights, but we'll see what's the intuition behind these weights. So given these nodes, which forms a coherent group with the edge weights of 20, 21, and 22, so let's try to add this node 4, which is very similar to the existing set, with the edge weights of 41, 40, and then 35. So we expect the overall similarity of the new set, 1, 2, 3, 4, will increase, since we are adding a node which is very similar to the existing set. This is also reflected by the fact that if you compute the weight, which is associated to node 4 with respect to this new set 1, 2, 3, 4, will be positive. So if, on the other hand, if we try to add a node, in this case node 5, which is less similar to the existing set, we expect the overall similarity of the new set, 1, 2, 3, 4, and 5, will decrease because we are adding a node which is less similar to the existing set. We are destroying the overall compactness, right? So this is also be reflected by the fact, like if you compute the weight, which is associated to node 5, with respect to the new set, 1 to 5, will be negative. So it turns out that these weights are telling us whether if it's a good idea to add a node to existing set or not. Okay? So in this case, node 1, 2, 3, 4 will form dominant sets since it satisfies the previous 2 criteria that we have shown. So basically finding a dominant set in this way is actually impractical, because especially when the number of nodes gets larger. But thanks to Pavan and Pelillo in their original paper in PAMI 2007, they showed that there is a one-to-one correspondence between finding a dominant set from this bigger graph and this linearly constrained quadratic optimization. So the one-to-one correspondence says as follows. So if you give me a set A said to be a dominant set from the bigger graph, if I compute the weighted characteristic vector using that set S, in this formula, the resulting x will be a strict local optimizer of this objective function x transpose x under the standard simplex. So the other way around, if you give me an x, which is the strict local optimizer of this objective function x transpose ax under the standard simplex, then if I take the support, which is the indexes of the positive component of x, which give me the indices in the bigger graph, which forms a dominant set. So by the virtue of this result, we transform this combinatorial problem of finding a dominant set from the bigger graph into a linearly constrained quadratic optimization problem. So to solve this problem, we have several algorithms which can do that in linear time, actually. So the other version or variant of this dominant set was constrained dominant set. In this case, we have a user-defined constraint, okay, given a node. So we are saying, give me a cluster which guarantees to contain this user-defined node from the graph, which is a very powerful property. We can achieve that by optimizing this parameterized version of the previous quadratic optimization that I showed you earlier, by subtracting alpha along the diagonal of the matrix A, where the vertices are outside of the query. So we have this theoretical guarantee that if we select alpha large enough than the maximum eigenvalue of the submatrix A, which does not contain the query, we are guaranteed that the solution we get will contain part or at least all or part of the constraints that the user defined, which is a pretty powerful property. So to solve this, as I said, there are several algorithms. Dynamics is the pretty famous one is the replicator dynamics, which evolved from evolutionary game theory, which has a computational complexity of order of n squared. It's very intuitive, very simple. You can write 3 lines of MATLAB code. You can get the solution pretty fast. So the other variant was infection immunization dynamics, which is also evolved from evolutionary game dynamics, which has linear time complexity. So however, these two dynamics, they require the whole graph to generate these clusters. So we propose this faster version of this constrained dominant set. So the idea behind it was like, rather than solving the clustering problem over the whole graph, let's select the subgraph B, say that the solution from the subgraph B is still valid solution over the bigger graph. So that's the bigger constraint. So we can achieve that if we are able to select a subgraph from the dominant distribution. So if we are able to do that, solving a dominant set from a smaller graph, we reduce the computational complexity of, let's say, replicator dynamics from order of n squared to order of r squared. Similarly, infection immunization will drop from order of n to order of r. Note that r is much, much smaller than n because it's a subset of n. So now let's see how we generate this subgraph and what this dominant distribution is. So the formal definition of this dominant distribution is as follows. So if you give me y, a distribution y from a standard simplex, said to be a dominant distribution, it should satisfy this inequality. So this inequality intuitively saying, if you use y as a solution, I will get a more compact set, a more compact cluster than when I use x. So this formula gives you the overall compactness of the result or the cluster, right? So in that case, y is a dominant distribution over y. I can get a better result if I use y, that means. So with that definition, we have this proposition, which says, given a matrix A, which is affinity matrix, and a distribution X, if there exists a node R which satisfies this inequality, that means the ith unit vector is a dominant distribution over X, so that which makes X is not a valid maximizer of our program. Okay, so for X to be a valid solution, so it should contain all the dominant distributions. So there should be no solution which can do better than X. So in that case, we have a theoretical guarantee that the solution from the smaller graph is still a solution over the bigger graph. So here is the algorithm. So at first, of course, we initialize X from the barycenter. That means we give equal probability for all the nodes in X. And then we will select the subgraph by using this formula. So the function S will give us, given a matrix and X, it will generate all the dominant distributions, and then we will generate this submatrix B from A using those dominant distributions. So once we have this submatrix B, we use B, and then we run our dynamics to give us a cluster from those smaller graph. And then this is an iterative process, and we go back and then check if that solution is still valid solution over the bigger graph. So we will repeat this process until there is no longer dominant distribution which are outside of our proposed solution. In that case, we will stop the iteration. So in practice, this iteration is pretty fast. It won't even last more than 3 iterations. It's pretty quick. So to show you some experimental results, we evaluated our approach on one of the largest actually data sets in multi-target multi-camera tracking, which is Duke MTMC, which has 8 cameras and around 2 million frames with 2,700 identities in it. So these are the matrices which are used to evaluate within camera tracking accuracy. So the green arrow shows the higher the beta, and then the red arrow shows the lower the beta for those matrices. So the last 3 ones are used to evaluate across camera performances. So this is the detailed result of all 8 cameras of within camera performances in easy sequences. And the last row shows the average overall average results. And you can pay attention to these columns since MOTA takes into account all other matrices. In MOTA, we are able to improve with around 10% overall average performance. So this is the result over hard sequences. Similarly, here also we are able to improve with around 5% over the state-of-the-art approach on MOTA. So these are across camera evaluations in test easy and test hard. We are persistently outperform in all the 3 measurements over the state of the art. Here in this case, we are able to outperform around 4% on IDF1 in both sequences. So to show you some qualitative results, so all these 4 people appear in all the 4 cameras, camera 1, 2, 5, and 6. So they appear in different times, but we plot them together for the sake of visualization. So as you can see, we are able to give this guy persistent labels throughout the video. And similar to this woman, we give her a persistent label whenever she appears in all the cameras, similar to this woman. And a few more challenging examples. In this case, as you can see, this guy appears in these 3 cameras, camera 5, 7, and 4. Even though he appears in a different pose, we are still able to give him the same label as he appears in all the cameras. Similar to this woman. Some more examples. So this woman has been given ID 371 in camera 6, and then we are able to re-identify her in camera 5 as she appears, and then we are able to give her a persistent ID 371 in this case. Later on, she appears also in camera 2. Here also we give her the same ID. So that's the overall objective. So we need to give a persistent ID throughout all the cameras. So there are more examples. So these 2 people with IDs 438 and 439 are shown in camera 5. Later they were recorded in camera 6, and then we are still able to give them the same IDs in both cameras. So in summary, we are able to formulate this multi-target multi-camera tracking as finding a compact cluster from the graph. And then we propose this novel fast constraint dominant set, which is able to improve the computational complexity in order of magnitude faster than the existing CDSC. And then we also outperform the existing state-of-the-art approaches over Duke MTMC. So thank you.